I'm Capiche.
I'm Taylor. I'm Simone. I'm Jaime.
And I'm Colin, and today we're going to be giving you a quick run through of atomic physics and talking about radiation and all that stuff. And it's going to be a good time, so sit back, relax, and enjoy.
Atomic physics is the study of atoms in an isolated system of electrons and a nucleus. It is mainly concerned with the arrangement of electrons, but we are going to talk about more than that. We will talk about the different atomic models throughout the years, atomic spectrums, electron waves, radiation, nuclear notation, half-life, fission and fusion, mass effect, and subatomic particles. All these subjects are important to the study of atomic physics, but for now, let's start talking about how the atom we know today came to be.
The earliest model of the atom was called the Billard ball model, and it basically said that atoms were just small invisible balls. In 1897, J.J. Thomson designed a model of an atom called the raisin bun plum pudding model. It was a positively charged ball with similar negatively charged particles scattered throughout. This is the first model that had a charge. Ernest Rutherford developed the next model of the atom. His model had negatively charged particles, called electrons, circling through the nucleus in a set orbit. An experiment to determine the model was shooting particles at a sheet of gold. Some negative particles broke off and either went through the sheet or reflected it. The gold sheet gained a positive charge. This proved that the atom was made of particles moving around it with a positively charged center. This would have worked if the electrons emitted electromagnetic radiation. When objects above a circular motion, orbit a circular motion, they have centripetal acceleration. The electrons do not emit electromagnetic radiation, so they cannot be traveling in a circular formation.
Niels Bohr took this model and said that electrons travel in an orbit at certain energy levels. Niels Bohr also discovered that at certain energy levels, light with protons of certain energy levels could be absorbed. This absorbed light creates black lines in a color spectrum. Each different element absorbs different energy levels and creates a different spectrum.
Louis de Broglie suggested that since waves act like particles, particles could act like waves. He took the formulas for momentum of an object and the momentum of a wave and put them together. He created the formula lambda equals h divided by mv, with lambda representing wavelength, h meaning Planck's constant, m as mass, and v as speed of electron.
Now we're going to move away from structure of the atom and how it's designed and move on to radiation, decay, fission, fusion, mass defect, detection of subatomic particles, and the standard model.
There are three types of radiation: alpha, beta, and gamma. Alpha is the weakest of all forms of radiation and can be stopped by something as thin as paper. Here's an example. Simone is about to be affected by alpha radiation. Luckily, she has paper. Capiche will be representing the alpha radiation and is currently being repelled by the paper. Thank you, Simone, for being safe. Now, Capiche will represent beta positive or beta negative radiation. Taylor has cardboard to protect her. The radiation was repelled by cardboard. Capiche will now also represent gamma radiation. Jaime will protect herself using a sheet of metal. Usually you will use more than a sheet, but it's still very effective.
In order to understand what happens to different elements due to radiation, we need to know about nuclear notation, which is referring to isotopes of different elements and the components of a nucleus. Isotopes are atomic nuclei that have the same number of protons but different number of neutrons. Protons are positively charged particles found in the nucleus of the atom. It is also known as the atomic number, the number of protons in the nucleus of an atom. All atoms of a given element contain the same number of protons. Neutrons are neutral particles found in the nucleus of the atom. Electrons are negatively charged particles that orbit the atom. The number of protons in the nucleus is equal to the number of electrons around the nucleus in a neutral atom. Atomic mass, also known as a mass number, is the total number of protons and neutrons in an atom. Nucleus are the protons and neutrons in an atom's nucleus. Transmutation is the process of changing one element into another. This occurs through the decay of that element. Later in this chapter, various forms of decay of elements will be explained.
In isotopic notation, X represents the chemical symbol, while A represents the number of nucleons in a nucleus, and Z represents the number of protons in a nucleus.
We have a number of conservation laws that apply to all nuclear processes. These conservation laws are conservation of momentum, conservation of charge, conservation of nucleons.
I'm never going to lose any weight. I'll keep my mass.
And conservation of mass/energy. In the process of alpha decay, the nucleus loses 4 protons and 2 neutrons to form a new element.
Beta particles are negative electrons emitted by the nucleus and have much higher speed than alpha particles. The basic negative decay occurring in the nucleus is your element turns into another element while releasing beta negative particles and what is known as an antineutrino. Beta positive is very, very similar. However, you have your element changing into a new type of element, releasing positive beta particles and a regular neutrino. Neutrinos have extremely small mass and zero charge. They were first suggested as a way to satisfy conservation laws, but have been recently proven to be correct. Gamma decay is the emission of high-energy photons from the nucleus. This often occurs after alpha or beta decay when the nucleus is left in an excited state. No change occurs to the atomic number or the mass number, and therefore no transmutation occurs during gamma decay.
Now let's talk about the half-life of an element over time. The amount of the element decays over time, and we can determine either the amount of an element we have had or how long it's been since the original amount began decaying by using the formula n equals n naught 1 over 2 to the power of t over t 1 over 2. N is the new amount of mass, n naught is the original amount of mass. T is the time since the original mass, and T 1 over 2 is the half-life of an element.
Fission and fusion deal with the combination and separation of nuclei. Fission is the separation of an atom by having it hit with a neutron. When the neutron hits the nucleus, it breaks apart and forms 2 new elements. And sets free some neutrons. Fusion is basically the reverse of this process. However, no neutrons are needed to fuse the atoms together. Neutrons are released when a new element is formed.
When binding nuclei, the combined mass of the 2 individual atoms is greater than the mass of the newly formed atom. Energy is released in the process, so Einstein theorized that the mass that was lost becomes energy, and he created the formula E equals mc squared, with E representing the change in energy, m being the change in mass, and c representing the speed of light. In order to make calculations simpler, mass can be replaced in the units of U, which the atomic mass unit is 1 U equals 1.6 times 10 to the negative 27 kg.
In order to detect the location of subatomic particles, scientists use something called a bubble chamber to detect them. Bubble chambers are chambers filled with water that is almost at boiling point and have 2 oppositely charged magnets at the top and bottom. When a particle is shot into the chamber, the particles release energy that heats up the water to the boiling point. The particle creates a trail of bubbles that allow the scientists to track the movement of the particle. The particle also travels at a curve due to the magnets. If the particle curved towards the positively charged magnet, then it was a negatively charged particle, and vice versa. Particles with heavier mass have a large curvature, and that makes it easier to detect.
So guys, what do you do when most of your theories have not been proved yet? You hypothesize more and go deeper. This is why physicists have determined if there were particles containing less than what is called the elementary charge. And that is how the Standard Model came to be. It describes and explains all the hundreds of different subatomic particles and complex interactions with 3 postulated classes of new particles: quarks, leptons, and bosons. Most of the existing matter around us is made from protons and neutrons, which at the same time are composed by quarks. Most relevant quarks are 6: up, down, charm, strange, top, and bottom. For each one of these quarks, there is a corresponding antiquark with the same but opposite charge.
Still, physicists have not enough with quarks and managed to discover even lighter particles, the leptons. In fact, these particles are so light that even if they have mass, they have not internal structure. There are 6 leptons, 3 of which have electrical charge and 3 which do not. The best known popular between the lepton are the beloved electrons. The non-charged ones are called neutrinos.
While quarks are very sociable and only exist in composite particles with other quarks, leptons do not like company. We can think of charged leptons as independent cats with associated neutrino fleas, which are uncomfortably hard to see.
Bosons are quarks and leptons' source of protein. Yes, they are force carrier particles and produce the full fundamental forces. Our universe exists because the fundamental particles above interact. Any type of force is caused by the attractive, repulsive decay, and annihilation interactions. Forces carried by these bosons happen because of these 4 interactions. We can differentiate 4 big types of forces.
Strong, which holds the nucleus together. Electromagnetic, which attracts or repulses charged particles. Weak, which are responsible for the decay of massive quarks and leptons into lighter quarks and leptons. And gravity, which are part of the which, apart from causing apples to fall from trees and causing headaches to scientists, allow attraction between masses.
Since these newly discovered particles were able to break that many rules, they accorded to obey at least our well-known conservation ones. That is said, they have momentum, charge, mass, energy, and even, if hard to appreciate, atomic mass.